Hello, I'm sorry I can't be there live, but thank you for letting me pre-record this presentation to you about Galaxy Zoo 3D with the subtitle Going Beyond Azimuthal Averaging. My name is Karen Masters. I'm the spokesperson for Sloan 4 and I'm a professor at Haverford College, which is in Philadelphia in the US. So this is really a celebration of the beautiful complexity of the galaxies that we have in the MaNGA sample. So here at the top, we have some images of galaxies with the bundle overlaid. And at the lower part of the screen, we have the emission line in H alpha. Here are some equivalent widths in H alpha and DN 4000. Just a few examples of the complexity and the non-axisymmetric features that we see in the MaNGA galaxies. Automatic detection of these features is improving. However, it's not yet accurate enough to do this full justice particularly with such patchy features and patchy data. So as a result, a lot of the really cool results that have come out of MaNGA have been as a result of azimuthal averaging, finding gradients as a function of radius. And so here are some examples of this. Here we have Belfiore et al. 2017 result looking at the radial gradient of the gas metallicity phases from Wang et al. In 2018. Here is a plot showing the slope of the radial gradient of DN 4000 against the central DN 4000 and separating those into different types of galaxies. And here is an example of the kind of radial binning that is used by a lot of results from this one from Ibarra Medel 2016. Those are just three examples. I've just pulled out a few more here. These are incredibly interesting results, but we're taking the full two-dimensional information that we have in our spatially resolved spectra and reducing it to just one dimension in order to make sense of things. So we thought it'd be neat to try to go a step further and to try to make use of the fact that humans are really great at feature detection. I've worked for many years now within the Galaxy Zoo team where we have developed crowdsourcing as a method to make morphology of galaxies reproducible and quantitative. So we thought it'd be interesting to use that technique to identify features in galaxies that have been observed by MaNGA. So our idea back in 2016 was to use the Zooniverse to develop a platform to crowdsource the feature detection in MaNGA galaxies. I worked on this back then with my postdoc Coleman Krozik, and also we had a summer student working on this, developing this project within the Zooniverse project builder format. We did a full project beta feedback, and we were ready to launch in March of 2017. So this is what the original Galaxy Zoo looked like when we launched in March 2017. You can still go and see the project at this website. I made a short version of it for you, but we are no longer collecting data. We have completely completed collecting data for this project. We had 4 different tasks within Galaxy Zoo. The first 2 were quite easy. We asked people to just click and mark the center of the galaxy and also mark any foreground stars that they saw that might be interfering with the MaNGA data. We then asked people to draw a box around a bar if they saw a bar in the galaxy. And we also asked people to draw spiral arms. This was a complex task, much harder, involving a freehand drawing tool. In the end, we put all MaNGA target galaxies through the site because we decided we just wanted to run it and get it done, and we weren't sure which would be observed at that point. But we did use Galaxy Zoo morphologies for pre-selection. So we only asked people to draw bars on galaxies where Galaxy Zoo morphologies had said there was a bar, and equivalently for the spiral. So there was some pre-selection there. Initially, the very first launch back in spring of 2017 went out to the entire Zooniverse. This attracted some pretty awesome attention. At our peak, we had over 100,000 drawings a day. This was the MPL5 sample, so it was a relatively modest subset of MaNGA, and we wanted to run this and do some analysis on it and sort of learn from the experience. We did that. We made some tweaks to the pipeline, some changes to the images that we showed to improve things, and we relaunched about a year later in February 2018. We relaunched only to people who had previously classified on the site, and that meant we had a much smaller kind of coming back fraction, about 22,500 a day at the peak for that, and that ended up taking about 6 months to do all the drawings on all of the MaNGA galaxies. Okay, so we have all these classifications. Now what do we do with them? And this has been led by Coleman-Krozik, who's still at Portsmouth, now also partially works for the Zooniverse. We collect 15 answers to every question, and these are combined to create a single consensus classification for each task for each galaxy. Coleman used a clustering algorithm to identify the location of the center of the galaxy and any stars that were indicated. And then for the bar and spiral arm tasks, we developed a count mask so that the users can then decide what threshold to use to determine where the bar and the spiral are. So if you want to see what that looks like, here's an example of an aggregation where we have a galaxy center in green. There's a foreground star outside of the bundle here, but it's still indicated. And then these orange and blue masks show the count, the pixel counts, so the counts here up the side of how many people included a certain spaxel as being part of a spiral or a bar. As a user, then you then pick a threshold in that to determine your unique spiral spaxels and bar spaxels. Okay, so let's look at these in a little more detail. Here is some example of the easy tasks, so marking galaxy centers and foreground stars. We haven't done a lot yet with the galaxy centers. The foreground stars, in the summer of 2018, I had a summer student basically look at the spectra of every foreground star for every MaNGA galaxy that had been observed already. And we determined that where more than 10 users identify a star, it's always a star. If the number is smaller than that, it's often a star, but not always. Sometimes they pick up H2 regions or other point-like sources in the bundle. So we think this threshold of n equals 10 is safe to identify foreground stars. And we want it to be very conservative because these foreground star masks actually go into our pipeline. So they are used to remove stellar spectra before the DAP runs. So we didn't want to accidentally mask out any parts of the galaxy. So those are in action in the MaNGA pipeline. And so here's an example. This is the image of the galaxy. Here you can see the center and 2 stars marked in this, the red and the blue here. The image is flipped. And here you have the DAP output with those star masks applied. And we're able to get this nice H-alpha flux map working without the fitting all have gone broken and stuff. Okay, so our medium task was drawing rectangles around the location of bars in the bundle. So we did this again, I remind you, only for galaxies where Galaxy Zoo 2 had identified a bar. And so here's an example of one of these masks. Oops, and there is that's the full H-alpha spectra, and that's just the H-alpha flux just from within the bar. These have been used by a number of people, particularly Amelia Fraser McKelvey. So here's a 2019 paper from her where she shows this bar mask that she's used and then the sort of inter-bar region in this one galaxy. She picked a threshold of 20% of users indicating that a spaxel was a bar to identify bar. And she was able to show that there were flatter age gradients in bars inside the bars than at the same radius in the inter-bar region. So that was interesting. Amelia also used it in a later paper in 2020, looking at the ionization mechanism for H-alpha in bars. And so about 20% of bars have significant H-alpha flux, and of those, 95% are star forming. And she interestingly picked a slightly different threshold for identified spaxels in the bar. There's no right answer there. You just do what works for your science and what makes sense. Dinesh Krishnarao, DK, has also used the bar masks in this paper, looking at the Milky Way analog sample. He's been using it in a more recent paper as well. Here he was able to show that the gas in the bar tended towards increased liner classifications, and he found these star-forming rings at the radius of the bar, so you can use these masks to identify bar radius as well. So that's interesting, and another example of it in use. Finally, we had the hard task, drawing spirals. So you had to use a freehand drawing tool to do this. Again, we only showed Galaxy Zoo 2 identified spirals, and we think we'll have about 2,000 galaxies in the final MaNGA sample with these spiral masks. So here's the example of the full H-alpha flux, and then just showing it in the spiral mask for this galaxy. Tom Peterkin has used these in a couple of papers. In this one, he just used them to illustrate the location of the spirals in this galaxy, where he was able to show using a Fourier transfer method that there is an offset between the H-alpha indicating current star formation and the blue part of the spectrum, the young stars in the spectrum, that correlated with the pattern speed of the spirals. So that it's basically evidence for a density wave. So you have the H alpha first, right after the density wave, and then the young stars a bit later. So that was a really interesting result and a nice use of the spiral mass from Galaxy Zoo 3D to illustrate the point. Again, in this 2019 paper, Tom Peterkin also used the spiral masks. Again, so this was about time slicing of the MaNGA disk. So making these little movies showing metallicity and metallicity of different types of stars, I think, as a function of time. And so again, he's using the spiral masks to indicate where the spirals are in this movie so that you can kind of orient yourself. Michael Greener is another Nottingham-based person, also uses spiral masks here in his result looking at dust attenuation in MaNGA galaxies. Interestingly, the result here was that there didn't seem to be any difference between dust attenuation in the arms and the inter-arm regions, even though in these dust maps you can still make out the spiral structure. So I think that's interesting, and we wonder if this maybe is to do with the 2.5 arcsecond resolution sort of beam smearing effects, or possibly some kind of bias of users, being more likely to identify spiral arms if they're bright and less likely if they are dust laden. I've also had a student using these spiral masks. So this is Shuaib Shamsi, who's a senior now at Haverford. He's writing his senior thesis on this project, where we've been looking at the fraction of star formation that occurs in spiral arms compared to inter-arm regions in spirals. Here is the percent of that total star formation in spiral arms within one effective radius. I'm showing that about half of the spiral, the star formation rate is happening in the spiral arms. And we're looking at trends with radius and with mass. This is still work in progress, which we have started including covariance between spaxels in the errors and in the summing. And we're continuing to work on this as Shuaib does his senior thesis this year, ready for graduation. You are all invited to use the Galaxy Zoo 3D masks and data. We've put it all right now. It's on the SAS, and you can access it through this wiki page. There's some example code, both written by Coleman and a version of it by me, where I've mostly put together Coleman stuff and sort of narrated it in a Jupyter notebook. You might like to talk to various users, so Shuaib, Amelia, and Tom Peterkin, and DK, other people I mentioned in this talk. There's, I think, a few others too. Hoping to release this as a VAC in the final data release for SDSS-IV, and hopefully I'll have the paper that describes the project ready for submission sometime in early 2021. So thank you for your attention, and thanks to our contributors in the Galaxy Zoo 3D project. Also a big thank you to Coleman Krozik for his work on the aggregation, and Shuaib for working with me on this at Haverford. Wanted to mention the other summer REUs, summer undergraduate students who worked on the project, Alex Todd, who worked with me in Portsmouth, and Daniel Finnegan, who came to work with me through the Keck Northeast Astronomy Consortium. And a big shout out to Marvin. So most of the analysis that you've seen here builds on the tools that are provided to us through the Marvin interface to MaNGA. So we couldn't have done it without them. Thank you for listening, and I'll take questions in the Slack channel, not live, but I'll be there tomorrow, and if you ask in advance also. Thanks again, and bye.